Hey there, mechanics friends! It's the beginning of the semester and it's time to rush your favorite fraternities, and I'm out here to tell you that only the sheer losers rush in Tau Gamma. You really got to join the best fraternity, which is Sigma Epsilon. So I hope you guys rush Sigma Epsilon today. Anyways, we're going to tell you a little bit about some of the things we do at Sigma Epsilon. Some of the things include these objectives. Define and explain the importance of ductility as it relates to engineering materials. We define Poisson's ratio for engineering materials. We'll also extend axial stress versus strain relationship to shear stress versus shear strain. And finally, we're going to apply Poisson's ratio to solve some engineering problems. If that sounds like a place you want to be, then come join us today. First, we gotta get started with our first objective, talking a little bit about ductility versus brittle materials, right? So you probably already have a sense for the difference between ductility and brittleness, right? If you don't, I have these souvenirs handy to tell you the difference, right? So I have this one and this one, right? What happens if I drop them? All right, I'm not actually gonna drop them. I don't wanna break them, come on. What do you think would happen? What's the difference between the two? Well, I feel like I can almost hear you screaming out that you probably said the glass one's gonna break, right? And the metal one's just gonna fall, it's gonna get banged around, and it's gonna maybe get deformed a little bit, but it's not going to break. So how does that translate to ductility, right? So when we talk about ductility, we say things like metals are more ductile because they have the ability to undergo deformation before failure, right? So if I drop this metal cup, it would get deformed, it would get banged, it would deform, but it wouldn't fracture. So that is kind of our definition of ductility, right? And then the opposite is true for brittle materials. Brittle materials like glass, when they fall, they break, they fracture, they undergo very little deformation prior to failure. Now, how do we measure ductility, right? We can go back to high school science or something, right? You probably are saying, oh, ductility is the ability of a metal to be drawn into a wire or something like that. That was some definition from physical science years ago. And it's kind of, it still holds true, right? Copper is a very ductile material because it can be stretched and pulled very thin. But how do we relate that concept into engineering? Well, in engineering, right, we want to have some sort of warning prior to failure, right? We don't want things to just reach their ultimate capacity and go boom, right? We want to actually be able to see some warning of failure. So ductile materials give us a little bit of warning of failure. I want you to just think back to last lesson we talked about stelia, right? When stelia was pulled, we saw that prior to failure, we saw a good deal of stretch, and we saw a good deal of what we call necking, right? The reduction of the cross-sectional area right there before failure. If that was in a real building, hopefully somebody would spot that and say something, oh man, we gotta fix that. As it happens, how do we measure ductility? Well, with that elongation or that reduction in cross-sectional area, those are two measures that we can use to kind of quantify ductility. All right, so we gotta get this ductility and brittleness stuff written up in your notes. So go ahead, get it written down, and then come back here and we'll talk about the stress-strain behavior of different metals and other materials. So we said ductility is the ability of a material to undergo substantial deformation prior to fracture. All right, so why do we want to use materials that can deform prior to fracture? Well, it's basically because we want to have some protection, some safety for our consumers, and also it provides us a warning of failure. So we said ductile materials will see that stretch, that elongation prior to failure, and so we can then do something about it and hopefully save some lives, or maybe we're even designing it to have a ductile failure. For measuring ductility, if we want to quantify it, we have percent elongation, which we went over last class, and we have the formula written there. We also have percent reduction in area. And so this has an absolute value sign just because reduction in area is always going to be a smaller area, so that's always going to be a negative number. Finally, we talked about brittle materials. We said this is characterized by stress-strain behavior that shows limited deformation prior to fracture. Welcome back. We're going to talk a little bit about the stress-strain curves for various materials, right? So I want to start with the basic kind of ductile metal, the steel, stelio, good old stelio from last lesson. So go ahead and we want to plot the stress versus strain curve for stelio onto this plot. So let's see if you remember how that went. All right. Hopefully you were able to remember what it looked like. If not, it should look something like this. This is our stress versus strain plot. So stress goes on the vertical axis, strain on the horizontal axis. So sigma and epsilon are variables for stress and for strain. And then we said for stelio, right, he was about a grade 50 steel. We said it had 4 parts. 4 regions. It went up in what we call the linear elastic range, and then at some point we started to yield. We said in the yield, for the yield plateau, we had increasing deformation or increasing strain without an increase in stress. Then the 3rd region we hit was the strain hardening region. It went up to a maximum, and then it started to have necking, and it came down and it failed. Now this was for stelio. Stelio was a grade 50 steel, so perhaps we would characterize that as what we call ASTM. They're our standard for testing in materials. So this could be an ASTM A572 grade 50 steel. This would be something common you would see in, at least in structural engineering and steel. This would be the grade that we would use. It's called a grade 50 steel because it yields around 50 KSI. So we would say Fy here would be about 50 KSI, kips per square inch. And so that's how we would characterize stelio. So hopefully that's what you got. If you don't remember stelio's test, go ahead and watch it here. All right, so again, we have stelio in the test frame, and we begin loading him up. We see that we're already, quickly advancing past the linear elastic range and into the yield plateau and onto then the strain hardening region. You can note the amount of strain, the amount of deformation that the tensile test specimen is undergoing. If you look at the top of the frame, you'll see that that is gradually moving upward, so you can see, visually see the amount of stretch that this particular specimen underwent prior to fracture. As we move through the strain hardening region, eventually we reach the ultimate stress of the material, and then we'll begin to see the specimen enter the necking region. So you see right in the middle there, stelio begins to fail, and then ultimately fracture. All right, breaks my heart every time to see my homeboy stelio get failed, but it happens, right? And all for our engineering knowledge. Now I want to talk about different types of steel. So we don't have just grade 50 steel, we have other types of steel. So let's say I have a grade 36 steel. How would you think the stress-strain curve for the grade 36 steel would look like? All right, hopefully you gave it a thought, hopefully you have some idea. Basically a grade 36 steel would only reach an Fy of 36 KSI. So it would yield somewhere around here. Now we have to make a determination. Would it be on a steeper or less steep curve? As it happens, steel, because of the nature of the steel, the modulus of elasticity is roughly the same for all steel grades. So even though we're going to have a lower steel, we're still going to increase at the same modulus of elasticity. And for steel, we take that modulus of elasticity to roughly be 29,000 KSI. All right, so for grade 36 steel, we would follow the same behavior in the linear elastic range, except once we get to 36 KSI, we're going to experience the yielding. All right, so we start to yield. So what's different between these two items? Well, 36 steel is a classic mild steel, and it doesn't have too many other elements in there to kind of trap the dislocations as they slide. Grade 50 is what we call high strength, low alloy steel, so it has other metals in there that kind of prevent the dislocations from sliding, which help then raise its yield strength and its ultimate strength. So we see that because it has less kind of things in it, it will yield, and it will tend to have a larger yield plateau than our Stelio did. And then it'll enter strain hardening just like before, and it'll stretch, and then it'll eventually fracture. And what we'll come to see is that a lower grade of steel typically has more ductility, right? So this is fracturing at a much larger strain, so it has a higher ductility than the grade 50 steel. So I just want to make that note that typically for steel, as our strength goes up, so as Fy increases or F sub U increases, then our ductility decreases. And we'll see that in terms of the yield plateau and then the total strain at fracture. All right, with that now in our mind, what happens if we used a grade 100 steel? Go ahead and try to plot the grade 100 curve with these two curves that you have and the knowledge you have already. All right, hopefully your answer looks like this. If you don't have an answer, you can pause the video. I'm going to go ahead and sketch the 100 KSI steel. That would be way up here in terms of our Fy. Our Fy would increase to 100 KSI. We follow the same modulus of elasticity for steel, so it just continues on up, the same modulus. And then it starts to yield. Now, we'll see that for very high strength steels that have special treatments, they've had special cooling treatments, this yield plateau becomes less and less and less as we keep increasing the strength. So we almost have no yield plateau, and it immediately begins to strain harden. And then we reach an ultimate value, and then it starts to neck and come down and breaks. Again, this would have a lot lower ductility than the previous steels. And so typical grade of this would be an ASTM A509. Oops, I always get my steel grades confused. This should be A514, not 509, so A514 grade 100. If you're actually going to look up the ASTM spec for something like a grade 100 steel. All right, so this is some of the different things about steel. We want to add here that we saw that an increasing Fy led to a shorter yield plateau. And a final note, we wanted to note that all steel has the same modulus of elasticity. All right, so now that we have steel pretty much down, we want to talk about aluminum. So I have Stelio's buddy here, Al, and we're going to test him next, and we're going to see how does aluminum compare to these values of steel. Let's think about, modulus of elasticity. How do we think aluminum is going to behave? What kind of strength? What about its stretch properties? Go ahead and take a guess. Pencil it in there as you watch this next test, and then we'll come back and we'll get aluminum plotted. So we have Stelio's buddy Al, the aluminum specimen, loaded into our testing frame, and we're ready to run a tension test on this. Again, keep your eyes towards kind of the middle top of the frame, and you'll be able to see the amount of stretch the aluminum undergoes. Please, whatever you do, don't forget the important measures of safety. So you can see here, I'm operating unsafely until I grab my safety glasses, so I hope I saved it. Make sure you guys wear your safety glasses when you're running your tension test, whenever you do that, for just to make sure particles don't fly into your eye. Alright, so we continue to load it, and you should be able to see a decent amount of stretch. You can see that the top of the specimen continues to elongate, so as we keep applying force. The aluminum's not quite as strong as Stelio, so if you recall, Stelio got up to 36.94 kilonewtons, and this reached a maximum of about 22.67 kilonewtons prior to failure. So a little bit lower stress, but the ductility is still there. We still see a lot of stretch, and right there we see the necking happen prior to failure, and so we have some good warning of fracture. Alright, hopefully that was exciting. Hopefully you enjoyed the test. Here's the aluminum sample as we had it, so you can see here's the amount of stretch in this particular sample when I pieced the broken one back together. If I was to pass this around, you could also experience aluminum. It's going to be lighter than steel, right? So I think we already have that concept, right? We don't use steel foil to wrap our leftovers, right? And we also use aluminum in things like aircraft and cars, right? Because we don't want to weigh them down with the steel. Anyhow, we saw that it has pretty substantial deformation, like a ductile metal. Aluminum is ductile. It has a decent cross-section reduction, and hopefully we saw in the video a decent amount of stretch. So let's go ahead and get aluminum posted. For a typical aluminum on our curve, we would say first we'll start at 0, 0. Now, compared to steel, aluminum has a lot less stiffness. So it's going to head up at a less steep slope. So that is why we prefer steel for a lot of our building materials, right? Because it has a very high stiffness. That means it won't deflect as much. A steel building won't deflect as much as an aluminum building. Plus, aluminum is more expensive, so it's also another cost factor to include. So aluminum will go up on a less steep slope. Now, where Fy falls for aluminum is kind of variable. It can fall around 40, 46, 50. So we'll just plot a typical aluminum in here. I'll take it up somewhere into there. Now, unlike steel that has a well-defined yield plateau, aluminum doesn't. It just immediately begins to strain harden. And then it'll go and it'll have some decent amount of ductility. Whether it's as much as this steel or a little less, I'm going to draw it kind of in this vicinity. Remember, this is just a typical plot, so this isn't, perfect. This would be our aluminum material. Remember, this E for aluminum will be less than the value for steel. Alright, so that handles aluminum. Now I want you to think about the next example, right? The next example we're going to do is Stelio's other buddy, Castile. She's a great partner, very, very strong. Actually, she's made of cast iron, but I think Castile sounds like a better name. Anyhow, what happens when we test cast iron? And so before we even think about that, think about where do we see cast iron, right? You probably have seen it maybe in like weights at the gym, or maybe a cast iron pan, right? If you're cooking or grilling or something like that, camping. So think about, how does cast iron, what if you dropped a cast iron pan, how would it break? How does that compare to steel, and how does it compare to aluminum? And then go ahead and take a look at this video. We got the cast iron specimen in place and we're ready to load it up. So like the other materials, we start in the linear elastic range. We continue to apply load. Looks like we're getting up close to about 16.7 kilonewtons. and boom, it fractured. Well, hopefully you guessed cast iron is very brittle, right? It's not a ductile metal. We saw that because as we tested this, right, we got up to somewhat of a low load and it suddenly snapped, right? If you take a look at the failure surface in there, we can see that for the cast iron, we have very little area reduction. It's not obvious where the area reduced before it just fractured apart. You can actually even tell if you can get really close. I have no idea if you can see that. But anyhow, on the fractured surface, anytime you see something like this where it's very brittle, very kind of grainy, that would indicate a brittle failure versus something like in the aluminum where we had some stretching shown and everything. This would be a more ductile failure. So anyhow, let's get cast iron onto our plot. Okay. Alright, so getting cast iron on here. Cast iron would increase. It has a, it's not quite as stiff as steel, but it's going to be close. It's going to increase, but then cast iron is going to be very weak. Somewhere in this vicinity probably. It's just going to fail. So we'll say this is cast iron. No ductility, no kind of curve, no increase. Just suddenly snaps. Alright, so hopefully this plot gives you kind of an idea of some of the different materials out there. We are talking in this class in Mechanics and Materials a lot about metals. So we'll be talking about steel, we'll be talking about aluminum, brass, those types of things, titanium. We probably won't really cover brittle materials like cast iron or other materials. You can save that for a future class. Alright, I look forward to talking to you next lesson. In the next lesson, we'll describe a little bit about how we can unload and reload these materials, and we'll talk about elastic and plastic strains. See you then.